Thank you very much, dear colleagues. Let's continue our work, the session of integration of science into production, future and prospects. Thank you to the organizing committee of MINEX, which for a number of years is organizing the session of this contents. I represent SNIGRI, Central Geological Exploration Institute of Non-Ferrous Metals. We are involved in precious metals, non-ferrous metals, and diamonds. It's most of the scope of work for geological exploration and survey, and we work in this institute, and we well aware about the problems in terms of scientific developments and making them applicable to practical use. And of course, all these issues are related with the application importance will continue to be important in future, and execution of these projects actually influence the efficiency of geological exploration. As part of our work, we have 6 presentations devoted and dedicated to the most promising directions. That is unmanned geophysics, which was already discussed here, and issues relevant to technological research, science-consuming endeavor, which was carried out by only a few companies. There will be presentations for use of laboratory equipment. We have 2 presentations of our Australian colleagues, which we are involved by integration of scientific developments into mining practice in Australia. I will not take more of presenters' time. I would like to turn it over to Alexander Parshin. Let's welcome him, Scientific Director of Siberian School of Geoscience, with a presentation how not to make money on unmanned geophysics and new models of junior business. The floor is yours. Good afternoon, dear colleagues. Thank you for the invitation. And this presentation is going to be discussed here at this session. I would like to tell the story not only from the viewpoint of business, but from the viewpoint of university, making a focus on research issues, which is called university science in the good sense of the word. And here is the slide. Everybody understands that the scope of work is becoming more and more difficult. More resources are required, and objects for research, it's becoming more and more difficult to discover. And so we need to look underground, and at the same time we have to go fast. And 15 minutes is quite a short period of time. So the basic topics of our presentation, the research and developments will make it possible to improve the economic efficiency of geological works. But at the same time, the companies, for them, is not profitable to provide the service for a cheap price. We actually, if we have serious geological competences, we can offer very high quality, and we can switch over to the junior type of business. And thirdly, the hypothesis, which I would like to defend, one of the most efficient conglomerates of companies who are going to use the services of university science. The first hypothesis, and was formulated in 2014, we could enhance the efficiency of the first stage if we plunge into the unmanned aviation with the carriers of sensors and reduce costs for geological studies of certain licensed areas. In this case, we will discontinue to use on-ground geophysics, and because we will choose most promising directions. And this is the part of geological geophysics. This is low-altitude technique, and the key peculiarity is the footage from small heights, and we execute this differently in our technological system. And in 2014, we didn't properly formulated it as a junior business because we didn't have the legal ground for that, and we simply thought it is the provision and support of scientific research. And we thought that we will just settle our scientific tasks. However, in 2016, the legal base was created, and we could enhance the quality and accuracy of the data. And the data from low altitudes could be much more accurate, and they are very well quoted and cited in the world temperature, 60 references and citations relevant to the drone aviation. And in order to ensure such type of effect, we had to accomplish a number of scientific developments. In most distant places, development of drone systems with a reduced level of systemic interferences, production of carbon to critically reduce the cost of such technologies. And if we're talking about the drone footage, you will spend your profit as a fee. But if you use it for yourself, you will make money. So this is the task which could not be solved by on-ground surveillance. Very often we don't see it in primary fields. Here on the top slide it is seen. Such abnormalities couldn't be traced by conventional means, but now we have the capability to map such types of objects. This is abnormalities taken from the height, on-ground footage, aerial footage, and here is the difference. Compare the results. And the geological missions are much simpler. So on-ground surveillance and aerial surveillance see the difference between the two. A lot of problems were found in different areas like gamma imaging, but here is the results. Small detectors are being used, and no specific methodology makes it possible, even using very light systems, to get spectrometric and radiometric data acceptable to process this information. And we see that this data is more detailed. It makes it possible to detect and find even small abnormalities, and you can see the difference between the aerial footage and on-ground footage. Radiometric imaging finds these abnormalities. Rosnedra were performed by this footage. Magnetic and gamma footage replaces the on-ground technologies. We also have different types of remote sensing to develop the digital model of the terrain, and these missions were solved. This is the second version of the system, which can fly for a long time with a loop of 50 meters. It flies in a certain selected area, and we are replacing on-ground electromagnetic measurements, very appropriate depths, and this data was already published in different scientific journals and magazines. And here is on the slides the results of UAV's TAM survey, and this technology makes it possible to receive 1,000 curves a day and replaces the on-ground footage. We are proud that these developments were highly appreciated by scientific community in the world. This is a comprehensive footage properly developing, and on the basis of a set of geodata and their quantitative interpretation, geochemical footage and imaging, and we could actually identify prospective areas for further exploration and very sensitive sectors for on-ground geochemistry. Again, the quality of inversion depends on the quality of information. A certain company acquiring a certain drone but with no competency will hardly be able to provide accurate data for you in order to properly identify the inversion. And with the help of these devices, we can go ahead and drill the sample wells. And different methods for the study is provided by the drones. And such technologies could be used, let's say, on the first dozen or 100 square kilometers, but in practice, the area could be as big as 500 square kilometers. And we see the probability of choosing the contour to identify the abnormality and to develop the data. And here are different perceptions of geologists to accomplish our project, and that could be done under difficult conditions of mobilizations, like steep slopes and swampy areas prevent from the large scope of works, which could be replaced by aerial efforts. It is a very environmentally friendly technology, and we came to the conclusion that we could discontinue to use the on-ground technology and develop the surveillance with the help of the drones. And less than a month, 2 or 3 people could get very accurate and highly detailed information, and they could sell it. And so the model of the mineral-based development should be different. We have chemists, geophysics, or geologists, and so we decided to discontinue the classical scheme. We don't have a stock exchange, and to switch to transform a scientific process and to plunge into the technological and junior business, selecting most talented students and involve them into the actual sites and deposits to improve their competence. We could create teams, highly motivated students accomplishing future tasks. And here is the field practice of students. Here is a geophysical or geochemical team which could perform whatever missions they might be assigned. And they might turn to be young professionals with good experience. They will continue to work in these endeavors. And this is the basic research efforts: sampling, mapping, small depth drilling, and that could be accomplished by this team. And young specialists, they find it very interesting and useful to work in such an environment. And here is the diagram which we offered to the Ministry of Science and Education. And here we talk that the basic moment of the junior activity is considered to be the university. It creates new technologies with the minimum costs to continue to develop the junior projects. And next year we could discuss their economic viability. And private company would find it difficult. We could plunge into scalable projects, collect original data, and that is a huge task to study a certain remote area. But students could do this job, and they could accomplish such large-scale projects. And of course, this is based on the intellectual power of professors of the institutes, and the university also had to be transformed to find time for different researchers, organizational work, deployment of drones, and the whole set of projects were accomplished based on this kind of approach. And our result from the viewpoint of junior business, financially, we could assess next year with no problem. Thank you for your attention, and I'm prepared to take questions, if any. Thank you, Alexander Vladimirovich. A very interesting presentation, both combining science and its application use, especially the capacity building in the branch. And the next speaker is done online, Nikolai Milovzorov. Are you online? Good afternoon.
Subject matter of the routine method of the impractical geography. You have the floor. Good afternoon, dear colleagues. I thank you and the organizing committee. You may, yes, you're fine. Go ahead. I thank you for the chance to speak at the forum, and I would like to use this time to briefly tell you about the application of scanning, electronic microscopy, and X-ray computer tomography in practical geology. In practical geology. Let me start with scanning electronic microscopy. Traditionally, objectives when you study geological samples and is over the 50 years old. The studies related to the composition, makeup of the minerals, use of applied tasks like preparation, seeking for zircons, using method ABC laser ablations. And as a result of such studies, we obtain a geological description of the sample, expanded in terms of elementary makeup. In many cases, it has a lot of wealth of useful information about changes in the makeup, which allows geologists to obtain all-around picture of their targets. However, since the science and technology are developing, we see now new instruments allowing us to do the study of geological targets in an automated way. Now we are able not only to obtain results from scientific centers in respect of specificities of formation of ore or rocks or minerals, but we can also obtain statistically valuable information about deposits and about the products of raw processing. We can get this information about the composition of tails and concentrates of the incoming raw materials. In order to address this issue, specialized scanning electron microscopes are produced. This slide shows you Intrascope TIMA. The history of application of this automated analysis runs into decades, and the key the pioneer Robert Scopson who was the chief mineralogist of the Andhra Platinum, who used 20 such devices to totally analyze both mineral raw materials and partial analytical control of the products of metallurgical processing. In order to understand how this method can be easily applied, I would like to give you some examples. We received a request from Russian geologists, gold producers, on a new plant. There were losses, and the geologists believed that the reasons for such losses of gold were sulfides, in which this closed gold was retained. The client produced samples in the shape of pucks, and he gave us both samples of irregular described. Only when he received all correct description of those samples, he believed in our results. As a result of this study, we came to the conclusions that in tails there is free gold, electrum. The size of the grains in the tails was different from 2 to 7 microns. In close gold was not in sulfides but in silicates and carbonates. No gold grain was recovered in sulfides. And we also attempted to measure the size of losses. It was 3 ppm. We could have given better analysis had we had more samples, and the samples were cut into halves. Then we would be able to make a better judgment on the surface of this sample. Such data helped a lot to our client in modification of the technological processes at their facility, and the tension in the relations between the management and the smelters refinery was removed. However, a search for gold, explorations for gold and silver was very quickly edged. Thin section we studied for not more than 20 or 30 minutes. However, the total mineralogical assay was done within the 2 or 3 years for each sample, and in each sample we contained about 300,000 grains of minerals. Thus, we have a method allowing us to very quickly, in a very short period of time, and in a verifiable manner, to obtain mineralogical analysis and to obtain a great deal of data, information about mineral makeup of the sample. We can identify mineral makeup in each fraction. We can aggregate results across all fractions. We can determine the mass share of each element, both in fractions, individual fractions, and in respect of the entire sample. We can get the detection of the opening of the grain after the crushing, which is very important for in flotation, and a wealth of other data which will take a long time to list. So geologists now and technologists now receive information enabling them to describe in full, in totality, and this information is statistically viable and repeatable, and the equipment makes it possible to create data, to create information about in the format of 24/7. So this is the workhorse capable of address such tasks. Thus, we can see that presently in the market such equipment is offered which can ease the operation of geologists. In particular, the equipment system test Cantima, which produces very high operation rate, has great verifiable degree of detection of minerals, and provide totality of output data. I would like to say that our company has demo laboratories located in Moscow and St. Petersburg. We conducted scores of demo studies, which we do free of charge to promote our equipment, and we invite all those who are interested in metallurgical laboratory analysis to come to us. These studies will enable you to get exhausting information about small fields, deposits in a very efficient and quick way, about man-made deposits, enabling your clients to provide information which they require. Now let me spend some time and describe the X-ray microscopy. This method can be found in laboratories, many laboratories. It has been there for scores of years. for the creation of medical computer-aided tomography. A Nobel Prize was given, but the first attempts for use this technology was not successful enough. Using medical tomograph scanner is a good instrument, but use of this equipment produced for scanning people limits our abilities. Other tomograph scanners, which are used in science and technology, do not provide good information. Micro scanners give good examples, but can be used only small samples, but they can't give us any information about how large a sample is. When, for example, we should study large cores in order to address the issues of the concerns of oil and gas industry, and to get the information about the direction, the propagation of fishes. We need to study large samples. That's why large specific scanners were developed, like the one shown on this photograph, which you get for 10 minutes. You can get information about full-size core, then can get increase the resolution so that you can get from large the whole sample go into detail and to obtain as a result exhaustive information about your target. The requirements in respect of geological scanner are as follows. It has they are listed here on this site. In particular, the scanner which we offer, and we conduct a lot of experiments, has greater penetrating capability because it has a wide range of voltage, accelerated voltage, and it has long service life. It has a great spatial resolution, which we can prove using standard samples, and we can show to the client the conformity of the piece of equipment bought by the client to the standard. The equipment is characterized by developed engineering solutions and can perform precision displacement of the sample of the X-ray source and the receiving pipe to obtain the section in the sample which we want to study. It's a very interesting example here is given on the left-hand side of this. One shows that when you study a core with the 100 millimeters in them, you can get the size of the grain 36 microns, so we can easily discern the say targets which may be 50. And if we enhance the resolution, we can get even see even smaller details. So that means we do a preliminary study of the core, and then we pick up the mode for detailed study, and in a non-destructive manner we study the sample. In so doing, the device operates very quickly, and if you want to study penetration of in the sample, we can do it. We can conduct experiments with good resolution in time 10 seconds. Thus, such equipment is offered to the market, which is specifically designed to study geological samples for dynamic experiments, and we are prepared to look at your samples and to show you what you can do using this equipment. There are a number of good pictures, computer animation giving you how we can present the mineral and the study, and we can see that some minerals which are present in small quantities can still be identified and calculated calculated in terms of their volume and quantity. And thus, I would like to reiterate my point, having a large input sample, we can, by increasing or say resolution, we cut out micro sample and study it in a scanner, and we can do a thin section and use the scanning electron microscope. And the range of amplification is 1 million. I thank you for your patient hearing. We invite you who are interested in the tomography and scanning in our demo laboratories in St. Petersburg and Moscow. We will be only too pleased to provide you as much information as you need and to conduct experiments together with you. Thank you, Nikolai Gennadievich. I think that we do have time for a question. If any in the audience have a question, we can use it. Ask to Nikolai. Good afternoon. Can we see a report about automated? Is it possible to see the automated report about the first slides? When you see automatic system of mineralogy, like scanning microscopy. So you did not give us any samples. So you see what data is output, comes in output. Next slide. Next slide. That's what you mean? This is a table, actually. In what shape, in what form shall we see this report? So you set in you pick up in the program, in the software, those data which you are interested in obtaining, and in the form of a table you upload it. So there's a mechanism of visualization. For example, particle species are visualized in your sample. Sometimes they're shown in different colors to give you an idea that different minerals are present in the sample, and then you can get diagrams, histograms, distribution in terms of the size of the minerals in the table, the degree of opening of each individual grains of mineral association. So you get a mass, an array of table data, which you then can upload into programs for flotation and to simulate technological processes. Some of our clients who tried our method, follow this way, they obtain good results. If you have any samples which you are interested to study, come to us. We will conduct a demo study, and we will get those tables which you need. Thank you very much. Thank you. Thank you for your question. Indeed, this does really work, and our company, our institute interacted with this company, and we conducted some. Nikolai Gennadievich, thank you very much indeed for your intervention. Thank you.
I hope Australia is online, and the next presenter is Marco Fiorentini. We are very happy to welcome you here. You hear us? So the next presentation, Marco Fiorentini, Deputy Director, Center for Exploration Targeting, University of Western Australia. And they are introducing those developments into the practice of the life of mining companies, the fundamental survey and applied arts. Mark, the floor is yours.
Добрый день, уважаемые коллеги. Can you hear me? Вы слушаете? Can you hear me?
Слышно вас, Марко? Все нормально?
Yes, Marco, we are okay, yes.
Thank you, Alexander, and thank you, everybody, for inviting me. My name is Marco Fiorentini. I'm a professor here at the University of Western Australia. I would have loved to join you in Moscow, but unfortunately, these days, it's a bit difficult. So I am going to use my time here to present, to give you an overview about the center where I work. I work within the Center of Exploration Targeting in the University of Western Australia. This is a center within the School of Earth Sciences, whose vision is to be recognized as the global leader in research excellence, innovation, and education in mineral exploration. We have a mission that allows us to apply scientific research to increase the efficiency of both the rate and the quality of discoveries carried out by mineral companies. And the objectives of our center is basically to really lower the risk, the large risk associated with the business of exploration targeting. We have a strong engagement with industry, and we pride ourselves to engage in research, in R&D with companies of various size, especially with major producers, emerging producers, and a very large base made up of junior explorers. The research capabilities within our center are wide and quite integrated. As you can see from this sketch, we have a number of core research capabilities, which include progressive risk and value, geophysics, structure and architecture, time scales and geodynamics, as well as geochemistry and metallogenic processes. Integrated with our mineral system science understanding, we focus on a wide range of mineral systems, including magmatic, hydrothermal, basin-hosted systems, as well as quite a lot of attention on critical mineral resources. The end product is to understand how we can engage with industry to have a sustainable resource supply. Later on in the talk, I'm going to give you an overview of some of the work that I've personally been carrying out in the geochemical and metallogenic space, showing the strength of our center and how I think our strength can be of use to you. I would like to emphasize, and this is integral part of this talk, the very important role that the state and the federal government, through the MRIWA process and the ARC process, have in favoring research. In fact, the state and the federal center, the federal governments, have a number of basically avenues to leverage industry investment into R&D, and that's what the center does better. For the ones who don't know the Center for Exploration Targeting, over the past decade, we've worked out to develop the concept of mineral system science, whereby mineral deposits are looked at as expressions of multi-scale earth processes, which focus energy and mass transfer at the range of scale. How does that translate into exploration targeting? The exploration for new high-quality mineral districts under cover basically can be eased, can be facilitated through the understanding of the largest scale footprint that these systems leave behind. And this is what our research is focused on. These large-scale footprints basically differ substantially from the local expressions that are captured by traditional analog models. And this is very important because if we develop the science, as we are trying to do, that allow us to understand which are those processes that really focus energy and mass, we can clearly move away from an understanding of mineral systems that is analog-based and move towards a process-based understanding, whereby orogenesis basically is developed, and the intersection, basically, it's between fertility, lithospheric architecture, and favorable transient geodynamics. This is extremely important because the key drivers of our centers lead us to basically think wide and broad into how we can resource the future of humankind, maximize the power of prediction and detection in exploration targeting towards zero waste mining. And this is important because that pushed us to understand or to basically envisage what do the ore deposits of the future look like. And I think we can all agree that they will definitely not look like this. We are all aware of the external social pressures and the fact that we are living in an increasingly energy-constrained world. Therefore, R&D, research and development, that is carried out by the Center for Exploration Targeted, but similarly to a number of other centers in Russia and globally, we need to change the definition of ore. Ore deposits will look different in the future. We need to focus, and our research needs to focus on high quality deposits. And in order to understand that, we need to focus on innovation. And again, as I said just before, move away from an analog-based approach. Ore deposits of the futures actually may not have any current analogs. It may be challenging for us to find them because we commonly find what we are looking for, and an analog-based approach has been useful and has been sustainable and has been successful in the past, but may not be helpful to look for the systems of the future. In fact, our heuristics and pattern recognitions allow us to basically find what we're prone to already know or to basically recognize. But the ore deposits of the futures may not have any known analogs. So how do we go about exploring for these systems? And most importantly, how do we go about providing industry and exploration companies with the right tool to go about it, about predicting and understanding what these systems may look like? In order to do that, I mean, this is obviously a topic that can't be exhausted in 15 minutes. But I provide here a series of just very simple examples of the type of research that we are carrying out here at the center. And I'm focusing on geochemistry, which is really a ligand for the various research streams that occur here in the Center for Exploration Targeting. Geochemistry allows us to map proxies for processes that focus that energy and mass transfer that is at the core of any mineralizing processes at a range of scales. And that's why I think that the success that the center has had over the past 30, 40 years is looking at applied problems with a fundamental science eye. The philosophy behind this is that at the core of any applied problem that the exploration industry may have lies a fundamental question that can be addressed through fundamental research. And as an example of the type of research that we've been carrying out, I'll just give you some examples. For example, our students, this is a training center, are looking and focusing on the planetary cycle of metals and volatiles. And we're looking, for example, at the physicochemical role of water, carbon dioxide, and other volatiles in the physical transport and concentrations of metals in the lithosphere. This type of work has earned us a number of Nature-like publications, but at the same time, the outcomes of this work have been actually routinely utilized in predictive exploration targeting by a wide range of our company supporters. So you can see here, looking at unraveling the cycle of elements at the lithospheric scale, and at the same time understanding within the lithosphere which are those domains that are more prone to contain concentrated metals environments. We have been developing, for example, isotopic tracers, and being based in Western Australia, for the geologists among you, you may know that quite a lot of our crust here is Archean. So we have been developing sulfur isotope-based tracers that allow us to trace and define chemically conservative and indelible tracers that may help us follow side by side a wide range of mineralizing processes. But by doing so, we also understand that and track interactions between the solid earth, the biosphere, and the hydrosphere. As an example, we have been looking at the sulfur cycle in the Archean, and we have been understanding providing insights about ore genesis and the genesis of komatiite-hosted nickel sulfide systems. And at the same time, we've been analyzing the changing and the varying composition of the Archean atmosphere. Again, fundamental science solving a fundamental problem, having applied outcomes that may be routinely used in industry. I'm going very fast here, but I would be obviously very happy to address any questions that you may have on the topic. Staying on the topic of isotopic mapping, but focusing on radiogenic isotopes, we have, for example, been looking at how metal endowment in lithospheric blocks changes through time, and at the same time, the genodynamic evolution of the early Earth. Again, understanding something fundamentally on how the Australian craton, and we've started with the Australian craton, but we've done a similar work elsewhere globally, how that has occurred, and at the same time helping industry focus and predict areas of the lithosphere that may be more endowed than others. Moving on, we have been working, for example, at the link between early life and appearance of life on Earth and metallogeny. This may, to some of you, sound as two topics that have nothing to do with each other, but by understanding actually how life first emerged on our planet, we are actually further understanding how some of the metals may actually behave in certain specific conditions. So our research is actually informing on the search of life in the solar systems. We're collaborating with NASA and ESA, and at the same time looking at some of how of the most important base and precious metals can be concentrated in specific environments. In doing so, we actually have looked at the metallogeny on Mars by starting at ferropicrites in the Pechenga region of northern Russia. So again, the mineral system approach that we have developed has allowed us to draw very broad comparisons between the environment on Earth and how ferropicrites may become mineralized in terrestrial environments, and predict the potential localization of nickel sulfide mineralization on Mars in different environments. We have been from a more practical, the examples I provided so far were more to do with the prediction of mineralized environments at the regional to cratons-like scale. But we've been working with companies to develop exploration tools for mineral systems. We have quite a lot of work involved in the detection of sulfide saturation in a wide range of magmatic processes, as well as utilizing some of the techniques that actually have been discussed earlier on in the MINEX conference. We have been looking at how to enlarge the hydrothermal footprint of notably very small magmatic systems. In doing so, we have also looked at the potential of the trital record to unlock the prospectivity of a wide range of mineralized areas. And this type of work may be actually very applicable in countries such as Russia, where specific type of mineral resistates are actually much more resistant. This is the last one, so I'm
Marco, I apologize. 1 minute left.
Finished for once I'm on time. As I said, I really appreciate Alexander's invitation here. Collaboration is key to success. Our center would welcome engaging with other research centers in Russia, as well as with companies presented there. And I'm open to any questions that you may have.
Большое спасибо, Марко. Ну, времени, к сожалению.
Thank you, Mark. Unfortunately, we don't have any time for questions, but we're very happy to see you. It's been a long time. We haven't seen each other. I know you like Russian very much. You're always welcome. And thank you for your great presentation. We carry on with our agenda. The next presentation is prospects of application of modern scientific research while doing prospecting and exploration. Evgeny Naumov, Deputy General Director of KBG, is on the podium. Colleagues, good afternoon. I will do my best to fit into the time slot given to me. I am happy to offer you a presentation about the future of the application of the results of modern scientific research in geological exploration application. This is a review. We will do our best to go back in the past about the past history of the methods which are presently used, and maybe make some predictions. So I work in the SNIBGU. This is a research institute specialized in the research for diamonds, base, and precious metals. This slide gives you an idea about the key functions of our institute, and we develop prospective methodologies of our exploration, geological exploration aspect of the diamonds, non-ferrous, and noble metals. We have developed a wide range of methodological recommendation. Some of them are listed here, but on top of that, there are a number of work which is now still at the inception phase, but I would mention them briefly. Thanks to Swoboda technologies, one can access the site of our institute and obtain more detailed information. So why is it necessary to have fundamental discoveries, and how technology affects geological exploration and defines actually all those new capabilities, thanks to which we can develop new or improve the existing methodologies of prospecting, exploration of ore deposits. The majority of the methodologies appeared in the middle of the 20th century, but they became accessible later, after some 30 or 50 years, following their development, thanks to simplification of their use and lesser price of the application due to development of computer technologies. This this diagram gives an idea as to how the number of new discoveries worldwide in respect of all solid minerals as compared with expenses for the exploration until the year 2015 was two graphs correlated very much, but then there was a peak rather, or spike, if you will, in the red line, as you can see, when expenses grew enormously, but new discoveries did not follow. And that there are a number of reasons to explain this phenomenon. Among them are the following. This table gives you the situation of the field, new existing technology trends about the exploration of new deposits of non-ferrous materials are shown here. Richard made them available. The number of the fields were discovered recently by more than 10%, and those who are on the surface decreased, and majority of them were discovered in known mining areas, regions. So in terms of the methods, situation is very interesting indeed. The number of fields grew, discoveries which were discovered due to prognostic models of the fields and conceptual and theoretical geology, which is being developed very rapidly presently, and which was something when Marco Fiorentini referred to only recently. And the second second trend, if you go back into the past, we will see that the majority of the deposits were discovered using geochemical methods up to 74, and earlier the share was even higher than that. But in the year 2008 until the year 2018, there was a great reduction of the role of geochemistry down to 54% in terms of discovery of many discoveries. And let me spend some time discussing the geochemical. Geochemical methods of exploration of solid minerals appeared in Russia. The first documented case of application of this method was done in 1917. And then the certain successes were necessary in the analytical area, and thanks to which such methods were developing very successfully. And in a couple of decades, our institute published a special set of instructions as to how metallurgical methods should be used, and geochemical method of exploration for minerals was introduced as an obligatory part of all prospecting and exploration work. But in fact, it started to be applied in the years 1960s and 1970s. That was the peak of application due to appearance of the matching analytical equipment. So we may see about 40 years, more than 40 years elapsed since the exception. It should be noticed that our foreign colleagues began to use geochemical methods later after the Second World War. I found an article dating back to 1949 in the Journal of Economic Geologists, a review about the achievements of geochemistry worldwide, and the author refers to Soviet work in this respect. And what else happened over this time when geochemistry became a popular method of research and exploration? Analytical equipment evolved in a very big way. In the same article, found information saying that spectral analysis was conducted using a portable device which could be transported using a car or truck. And now this portable piece of equipment is handheld actually. As you can see on this photo, you can carry it by using your back. So this is a kind of evolution which had occurred in the domain of geochemistry. But now we can see, maybe due to the fact that all discoveries which could be discovered using classical method have already been discovered and are now being developed, and the role of geochemistry is reducing. Against this background, we see sharp development of modern geochemical methods, which are based on the modern analytical approaches. In particular, one of such methods developed by our institute, and majority of those methods based on this isolation by various reagents, metal from thin fraction of the subsoil water. MMA technology in particular. In our institute, we developed a method of ion sorption, which is widely known, has been used quite widely and successfully over the period of several years. In our institute, a lot of work, papers were devoted, written in respect of this work. In particular, this survey was done in the Bologoye deposit of non-ferrous metals. So after the period of testing, now it is widely used for exploration for massive polymetallic ore, which is something which you would expect to find in Kazakhstan, in Altai. This method is being updated now, refined now, to make it suitable to use for in the exploration of gold. But there is a huge future for those methods. They're quite sensitive, and through secondary and quaternary sedimentation, they can sense the ore where the classical geochemistry wouldn't work. One more method which is very progressively used in exploration, in the prospective exploration, this is a study of the composition, makeup of the gold. The criteria of this method is as follows. It can be used as a criteria for formation association of the deposits, and also as a marker of the chemical and physical conditions of the formation of the mineralization occurred. The methods were concurrently developed both in Russia, in the Soviet Union, and abroad, and you will see a paper published in 1993 dealing with the, relations of the use of the gold associated with the copper and porphyry system. Using morphology, you can define the appropriate distance from the source, and having studied the composition of the natural gold, you can make a conclusion about the formation type of the deposit and about the level of erosion section. Analogous work was conducted in our country in respect of the mercury-associated gold. Such work was then used in micro-zone X-ray spectral analyzers. And thanks to a great number of statistical data obtained, so in particular, more than 30 deposits were studied, more than 2,000 results of analysis were obtained and processed. One can propose what is the formation source we are in search in respect of the gold. And our institute also conducted an integrated study which enabled us to identify new morphological tracers. We used more indicators in this respect and more elements of impurities, and we obtained the great statistical data. More than 120 deposits was started. This data have been published. They are not known much in the West because they were published in the Russian language periodical journals. Let me spend some time speaking about the modern methods applicable to the subject matter of my presentation. You have 3 minutes to go. Well, I have 4 minutes. That's what my watch says. Okay, this is the study of the minerals, traces of porphyry minerals. This is a well-known method. And now we are in our institute working doing some studies. We are studying accessory minerals of the porphyry system, when we can make any conclusions about the perspectiveness of a particular system. Let me say a few words about tomography, which was covered by Nikolai Milobzorov. He produced the producer of this tomograph. But if you look into the past, you'll see the first prototype of tomograph was presented in 1971, and after some 40 years, we now have a geological application of tomography, X-ray tomography, as you well know. It's based on X-ray study of samples. We studied them, and you can study samples which are placed in a tomograph. Normally, this is samples of the size of a core, and we conducted studies on the nano level. So the benefit of this method is that you can look into the method using non-destructive methods. You can look into the arsenic and pyrite and see the natural gold. By analyzing it using different methods like mass spectroscopy, mass ablation, we can get the details of its chemical makeup. And generally, our experience shows that we can assess the inclusion of the natural gold into the matrix of the host rock. It studied the laws of its propagation, and if you apply complex methods, it is possible to find the form of the occurrence of the metal. And for technology, it's very important we can see visually where the metal sits in order to understand it. So this was the local tomographic methods, but now we see technology, development of technology which is based on the breakthrough of the fundamental physics. We can make a tomographic scan, not of a sample basically, but of a large section area of Earth. This is the so-called muon geotomography. In respect of geology, this work are done only in a very short way. Beginning with, so the first work was done in 1965, and methodology was started to flourish at the beginning of 2000. In 2008, planned surveys of geological targets started, in particular of volcanoes, and this method is based on study of on registration of muon, these high energy cosmic particles which constantly come to Earth from outer space. In order to register them, it is necessary to use very serious equipment. Our colleagues from Canada in particular use their sufficiently bulky detectors to placing them under the deposit of polymetallic ores, and as a result, without any drilling, they obtained a 3D image of ore bodies. The accuracy of this method is still left much to be desired, but starting from the 2014, when this work was published, 6 years have elapsed, and new information have surfaced, and commercial applications of this methodology now come into being. Well, this slide gives you an idea about what it can do. This method is used to use massive sulfide-based deposits made with massive sulfide ores. This method offers great economic and then ecological impact. We can reduce the extent of core drilling, and on top of that, the damage to the environment is lessened. The method is has great future. Now it is being developed, as I mentioned. There are a number of very large and powerful scientific groups. They are listed here, which conduct research in this area. I believe within the span of, say, 15 years, we'll be able to see great results. This method would be up and running, which we will be able to apply it to address our tasks in terms of geological exploration, prospecting exploration. And in conclusion, I would like to cite some language from a sufficiently old publication in a magazine, which was on a journal, 1949. I will read it out. It says, it is too early to predict the final place of geochemical study among other methods. at the early stage of any technique, it's possible to place too much enthusiasm into any new methods. Geophysical method of exploration in the first phase of the application were overvalued, and as a result, they have bad geochemical methods should be spared. After some 70 years, this conclusion is still valid and topical, and we now conduct other methods, but still it is, I fully agree with the author that one should look at new methods in a wise and a reasonable way. Thank you for your attention, and thank you for staying too long on the podium.
Thank you. We don't have any time to ask questions. Should you have any questions, please come to him directly or write through the email. Now we'll turn it over to the next speaker. This is an online presentation. Our Australian colleagues, the head of the research scientist, Mineral Resources and Water, Perth, Australia. Walid Salamar, are you online?
For giving me the opportunity to present today at the MINEX Rush Forum. The main topic is about digital science vision for the future exploration resource extraction in the digitalization era. My name is Walid Salamar, team leader of minerals and water at CSIRO Mineral Resources in Perth, Western Australia. Before we go, I just would like to introduce you to the topic. This is a very broad topic today. I will just give you a bit of introduction about what we're doing here in CSIRO about the technology we develop. Number one, the mineral resources industry faces a unique challenge for locating all the ore bodies. CSIRO is embracing digital technology to improve data collection and make surveying of the most isolated area more efficient, easier, and cheaper, and safer. Sensor and automation are revolutionizing all aspects of mineral discovery, mining, and processing. And we need new sensors and sorting technology to increase mining productivity and safety. Automation also in mining is reducing hazard and removing workers from harm. Automated analytical systems are helping acquire and process data across minerals value chain, delivering faster and more reliable results. We also here, I'm talking in this presentation about two digital tools we have here in CSIRO, and we focus mainly on mineral resources business unit. The first one is mobile apps and drones. These two technology could transform mineral exploration in Australia and also around the world. One of these tools is actually a mobile app called Field Acquired Information Management System Mobile Field App, or what's abbreviation is called FAMES. FAMES improve data quality, accuracy, consistency by reducing human error during recording and transcribing. It even reduces barcodes to stick onto sample bag in the field. So researchers don't need to write ID or other detail on them. The app automatically uploads data to a portable server, which increases data security and makes it easier for researchers to work on a very remote location, because they don't need any Wi-Fi or phone network. CSIRO also see drones as promising exploration tool, as they allow us to cover a relatively large area and provide data at much higher resolution than the aircraft do. Well, number one, which is Field Acquired, the FAMES app. The FAMES app is developed actually as part of the project called the Capricorn project, where we did a large-scale geological mapping and geochemical sampling, and that area is Capricorn here in the central part of Western Australia, actually the mobile data capture app developed as part of this project. When we go for that app, the most important thing to avoid the old way of recording data in the field by taking notes and the risk of losing the data later afterwards. So moving from the pen and paper to mobile app is the most important step. The app is available to download from Google Play. It's called Themes Project. You can just look for it in Google Play and you will find it. Actually, it looks like that. We use normally in our exploration field trip. It looks like that. The app is adapted for CSR protocol for geochemical sampling, allow all of our geochemical data collection, basic mapping functionality. Photo tagging can be done, field printed labels and data matrix for scanning into the application sketches, site information, lithological descriptor. There's also a field server provided to prevent data loss and syncing with multiple devices. All the hydrogeochemical samples and also rock and soil samples are now collected in this way, and it's open source, so we are happy to help others as well in that type of the app. VMs also here, you can see it on the tracked server for data management in Outlook, syncing server, Wi-Fi network, and data backup. Here for some basic mapping functionality, for example, that's example for the soil sample over satellite imagery. You can push button to find your location with GPS, taking photograph, and also we can create shapefile that can be used later on after the field. Also, we do sample. You can also look for sample generation project detail screen, which is this part on the left, and data acquiring for sampling editing if you need to do some editing later on the right. Also, this, as I mentioned before, it has been taken with the various parameters and input into the app. Some for water sampling and other for rock and soil sampling. We add all the information required. What you need to go is just recording all your information quickly on the app and come back, and you'll be sure that everything is saved on the server. And that's an example. You can also download the data output on your computer and also get all the files on your computer, and you can play it later on with any other software, something like a GIS, because we generate shapefile. It has been tested, this app, in the field, actually over large area in southern Australia, like a Kumbana, which we do a very big project, Kumbana Regional Geochemistry, that field test site. That's actually an area mapped of 80 by 50 kilometer, and by its very remote area, and also by airplane, collected sample from roughly more than 300 sites. Each site got, by using the app in the field, 6 minutes, which include 4-minute travel and 2 minutes for refill, and 280 samples at 4 kilometer spacing. That's 5 samples each site. Each site has soil, rock, and vegetation sample, and all integrated in tablet and have the QR code labels, as you see here in the ground here. Surface geochemical mapping has done 7 days, very quick, on 310 sites, analysis and field sample on the fly. That for the themes, which is very good. You can just see more details on the Google Play for that app. The second most important topic today is part of the presentation is sensor and automation. Sensor and automation are very important for the future for exploration and mining. The main reason for that, because the sensors have the ability to accurately measure valuable elements and minerals, which is critical for optimizing processes. CSR emerging sensor technology provides real-time result, opening opportunity to make significant cost-effective and increase mineral recovery rate. The main challenge that we know at the moment is measuring concentration of valuable minerals and elements on a real-time basis at all the stage and process. Faced with global competition and increasingly lower grade ore, minerals and mining operations are looking for ways to improve efficiencies and productivities. In order to be effectively improve plant performance, operator needs accurate data on key elemental, mineralogical, and physical information on ore at all stages of processing. So new digitally enabled measurement tool to aid decision making while make processing lower grade deposit more efficient and economically viable, while ensuring valuable concentration of metal are recovered and prevented from going to waste. Example from these technologies that produced by CSIRO and currently commercialized, each of which has their own advantage for different processing stages. The first one is called photon assay, which is technology which have a fast alternative to traditional fire assays that measure gold grade in core sample without chemicals in 2 steps. And also online gold analyzer measures ultra low level down to tailing grade for gold and precious metal online in real time. And the last one is an example of magnetic resonance technology for rapid copper ore sorting. All of this technology and detail about this technology are actually found on the website of Sensing and Automation in Mining at CSIRO website. The next topic is how we deal with the low-grade ore. We know that the mining and handling and processing of low-grade ore in mining and mineral processing is resulting in high consumable and capital cost, higher waste and generation tailing, and lower profits. While this is a widely acknowledged issue, solutions have so far been limited. Multiple opportunity for alternative solutions exist. Theoretically, it would be best to remove sub-economic material as early as possible during mining and processing. The theoretical options for achieving this are in situ recovery or in situ leaching, where the metal can be extracted from ore via solution with the bulk ore never moved. And also this process that you can target the ore by fluid, extracting fluid in place without moving the ore itself at depth. The second one is optimizing mining, which where the ore is well characterized and area of low-grade ore are not mined. Conducting some processing underground, example crushing, or to reduce the amount of ore transported to the surface, and the ore sorting at various stages of the process where the ore quality is measured and sub-economic material is diverted away from the further processing. One of the most important topic as well in the last 10 years and have a promising application in the future for mineral exploration and resource extraction are actually drones. Drones has been applied mostly in Australia and Africa and have been becoming popular over the last 10 years in support of mining application with exploration, surveying, and mapping. As I mentioned, Australia and Africa have led the way in adoption of unmanned aerial vehicle, which is abbreviated UAVs, across the mining industry to maintain safety, increase oversight, and enhance security. Drones normally use cameras, LiDAR technology, and also plugged into photogrammetry software. Also can create full 3D and 4D images and maps of wide expanses of land, contour lines, digital terrain models, digital surface model. The mine survey images generated by drone, camera, or LiDAR technology provide detailed information to assist mining operator with managing, planning, and optimizing production on the mine site. And the most popular uses of drone in mining application actually is stockpile management, where the volume of the placement of stockpile can be accurately predicted with mine area survey. Automatic surveying and mapping, as we know, the drone can be used on surveying and mapping of mineral landscape, which become quicker process with the use of drone. It's also monitoring of the road optimization. The efficiency of mining application is dependent on the road network, and road condition must be regularly monitored for safety, and also assessment before and after drilling or blasting is very important, because drone in mining produce very cost-effective and accessible 3D reconstruction along with a surface model to display the drilling or blasting site area. Also the hazard identification and mitigation, which related to safety, which is priority on any mine site, and drone surveying can easily identify any safety hazard with high-resolution images. Tailing dam management and mining exploration as well, where the mining exploration is supported with the use of drone survey imagery, particularly in the site area that are difficult to navigate by foot. In summary here, the mineral resources industry faces a unique challenge in locating ore body, and digital technology are required to improve data collection and to make surveying the most isolated area more efficient and easier, cheaper and safer. Sensor technology provides real-time results, opening a new opportunity to make significant cost saving and increase mineral recovery rate. Handling and processing low-grade ore in mineral processing operation is a great challenge for the mining industry. Drones have become increasingly popular over the last 10 years in support of the mining application with the exploration, surveying, and mapping. That's the end of my presentation, and thank you.
Большое спасибо, господин Саламов.
Thank you very much, Mr. Salama, for a very comprehensive presentation. We would be very happy to see you at the next MINEX of 2022, and the organizations which you worked for will provide some new results. Thank you very much. We turn it over to the next presentation. So the commodity products is the end of exploration process. And the next speaker will be done by Alexander Billy, in charge of laboratory leaching of the gold-bearing ores, BioNord technology on the
Dear colleagues, good afternoon. I thank you, the organizers of this forum, for an opportunity to speak. Can you see my presentation? We can see your face, but not your slides. Perhaps it will be activated. So far, we do not see your slides. Okay. Now we can see your pictures, your slides. Okay. Switch on the presentation mode, and then it'll be fine. So this is my presentation. Yes, I see your presentation. Now this is the title slide. Okay, thank you. So I present my presentation related to the development of BIOX technology using Olympiad BioNord. If we look at existing technologies in terms of gold extraction, we can see that I will simply sintering, leaching, beyond jokes, and so on and so forth. Generally, depending on the input material, the method is chosen in respect of the budgetary. In this case, we developed our own methodology, technology BioNord, which we use in our production facility. If we look at all the companies and production sites existing worldwide, we can see that there are a number of technological methods as BIOX, BioNord, BACOX, and CCRI. Generally, a majority of sites use BIOX technology. And here we have a list of all the largest existing sites. Our Olympic plant is ranked second in terms of the capacity and processing of concentrates. And the numbers can be seen on the slide. But in terms of gold production, we rank first because we produce over 30 tons of gold a year using BIOX technologies, BioNord technologies. Here you can see on this slide a review of all the production sites which use this technology. And we are located in the extreme Nordic conditions. We are 400 kilometers north of Krasnoyarsk, near the city of Verkhny Yeniseisk. This is where the Olympiad was located. And temperature in the winter goes down to minus 45 Celsius. Under these conditions, it is difficult to operate production. Many other technologies may not work in the other conditions. In terms of mineralogical makeup, the flotation concentrate we receive is a unique one because the key gold-bearing minerals are presented by ammonia, antimony, 45%, and by therapy, and you have some other. We should emphasize great content of pyritite with 25%. And the peculiarity of this composition is that when you use oxidation technology, a great amount of heat is determined. We need great cooling system to keep the process under control. The biochemical oxidation is based on the fact that certain association of certain micro bodies oxidize sulfides and the elementary sulfur, and due to this, all sulfides, key sulfides are oxidized, and the oxidation takes place in very rigid conditions. Well, the pH of our solutions is 1.9, 1.8, and at the high content of ferrum. So the oxidation is done by bacteria in our system, and chemical concentration due to high concentration of solutions of sulfuric acid as well. Our bacteria is made of a number of bacteria. There are about 10 in numbers of different types. You can see the list of those bacteria on this side. And now, sustainable association of bacteria has come into force, and the process of bioxidation is very stable in our production. The scheme of production of ore is as follows. Well, of course, we extract and we crush. Gravitation, say, separation of gold is gravitation tables. And then it is sent to the flotation. After the flotation, concentrate goes to bioxidation phase, which takes place within 96 hours, 100 hours. Then centrifuge, it's sent to centrifuge, and then goes to sent to the sorption. Following which sorption is used, for sorption we use carbon, and we have desorption, electrolysis, and we get doré ingots. The key parameters, production parameters, are as follows. The productivity of the place is about 1,150 tons per a day. That depends on the input material coming for processing about the ore. Technological scheme of the connection of reactors, we have 5 load and 1 tail reactor. The count of the solid material in the pulp, depending on the type of reactors, about between 190 to 260 grams per liter. And time of oxidation of concentrate about 100 hours. Number of dissolved oxygen is at least 2 milligrams per liter. The temperature of the process, 39–40%. The concentration of biomass in the liquid phase, 3 to 4 grams per liter. The reactors which we have, the 404 cubic meters and 1,000 cubic meters capacity. The quantity of the processed ore about 13.4 million tons per year. Now we're expanding this quantity. If we look at the phases of the development of this technology, the biotechnological methods, I would want to say the following. The first generation was Bio-1. It was commissioned in 2004. The reactors were 440 cubic meters capacity. We use piston oil compressors, which was not good, manual feed, and the pumps distribution in terms of the production shops was only one. And that shop 5 lines using 6 reactors. There were 30 reactors, and the volume was 440 each. Based on the studies in 2007, another BO2 next generation, while the capacity of reactors was 1,000 cubic meters. Each reactor has its own pipe, and there was distribution of the feed in a different way, since the line were made structured in one line, and the last reactor there was clogging of pulp, and we had to address it. Instead of oil compressors, we used turbo compressors. So the production activity was 400 tons per year, and when we commissioned BO2, we were able to process about 900 tons per year. Based on the experience gained on the second generation reactors, we commissioned Bio3, third generation reactors were the 1,000 cubic meters capacity each. So we had the BO3 6 reactors uses 1,000 reactors capacity. We use the automatic feed of feed and the tenacious supply of air. And finally, now we are operating the 4th generation Bio4, as we call it. You can see it on these pictures. This is the development from laboratory, pilot unit, the 1st generation, BO1, then Bio2, BO3. And as I've mentioned, the temperature is low in the winter summer, so that's why all our reactors are located within closed enclosures. The ambient temperature is low during winter summer, so generation 4 was different in such a way. So in order to reduce the expenses on the cooling system, we decided to place reactors in the open. We see the reactors are located in the open. Some of them are in the closed enclosure, so that the operating personnel have comfortable environment to work in, and to do the maintenance work if necessary. So this is the shop Bio4. It has, as I said, 8 reactors, which are 1,000 cubic meters cubic capacity each. We expanded the number. Now we have 10 reactors, as I mentioned. Presently, the productivity, when we commissioned the Bio4, about 1,050. 1,600 cubic meters ton per day. The reactors of this shop, we use mixers, Gig-Compenject, which we initially tested together in laboratory conditions. They enable us to mix the pulp in a more intense way and with great degree of aeration. That provided opportunity, if you look at this diagram, to decrease the power consumption due to redistribution of the power from the compressor to motors. We increase the power rating of motors. Here in the Bio3 work, we have 45 kilowatts. We have only 110 kilowatts. That made it possible for us to mix and aerate the pulp in the reactor, and at the same time we reduce the air consumption as well. This diagram gives you an idea about the concentration of biomass, which is one of the key parameters of the process, and you can see that during the commissioning, you can see that the biomass in the Bio4 is collected in yellow. It goes up 3 grams per liter. It goes up and up, and as a result of this, the process of oxidation of sulfide is intensified down to sulfuric acid, and that's why, due to higher, more intensive oxidation, you can see that in terms of Bio4 consumes the lowest quantity of sulfuric acid as compared with previous technologies, which you can see in Bio1, Bio2, Bio3. So, and indeed, the consumption of sulfuric acid is really low. Generally, as I said, we are producing about 1,500 tons of concentrate per day, and we produce about 30 tons of gold per year. We hold patents for the technology by North and for the association of the method of application of biotechnology, oxidation, also sulfide with the purpose of extraction of gold. Thank you for your patient hearing. Thank you, Alexander. I did not interrupt you because it was a pleasure for us to listen. Like Olympiadinsky Gok is one of our engine in terms of use biotechnology. Thank you very much for your presentation. And I would also like to thank those who have made it to the end of the session tonight. Without distracting anyone, and I understand I don't want to stand in between you and the cocktail party. A lot was information was given in respect of solid minerals. In our institute, we continue, we monitor, and we introduce new technologies. And if we look at the diamond, I would like to say that we have huge issue, crisis of technologies, ideas, and geophysics as it used to be, that is not applied, or if it's less effective, so we have to think about new and new methods, and that does not give us good result. In solid minerals, this is not the case. We do not we are not facing such complicated issues. Those presentations which were made today, and generally in MINEX and other sections, will make it possible for us to address the situation as it is now available, and to use the ideas and proposals which were aired in our exploration work, and to, with it to enhance the efficacy of prospecting and exploration, and to reduce, to mitigate those difficulties which we now face in terms of replenishment of mineral base. I would like to once again thank all the speakers and the presentations which were made today were good, and I would like to thank the organizing committee of MINEX, which every year brings us together and gives us a chance to speak up and to borrow new ideas from our colleagues, which definitely will be used in order to step on the fix our work. Thank you very much indeed. This is the end, brings to the end of this session. I wish you every success. Bye.